All right, well, thanks for coming out. Thanks for not leaving. Just a little bit of who am I in case we haven't met yet. My name is Bill. I'm an 18-year-old freshman. I love breaking stuff. I spoke at DEF CON and at Recon Montreal, and I'm really interested in Windows internals. So this talk is about bloatware, and it's already widely known that bloatware slows down your system and takes up unnecessary space. But this talk will be exploring a different kind of risk, and that's the security risk of leaving bloatware installed on your system, whether it comes from your manufacturer or you install it yourself. The vendors in this talk will be Dell and Lenovo. So the vulnerabilities in this talk are remote code execution in Dell SupportAssist, local privilege escalation in Dell SupportAssist, cross-site request forgery in Lenovo Service Bridge, and remote code execution in Lenovo Service Bridge. So Dell SupportAssist is advertised to proactively check the health of your system's hardware and software. Unfortunately, though, it comes pre-installed on most new Dell machines running Windows. The idea is that you can update your drivers remotely and conveniently, all from Dell's support page. The software itself does legitimately provide useful updates, but the major concern is that it comes pre-installed on newer Dell machines, making the number of endpoints potentially at risk significantly higher. So back in last September, a while back, I got a new Dell machine replacing my old MacBook Pro that was 7 years old. It came with a clunky hard drive, and I decided to replace it with an SSD. Part of that was reinstalling Windows and getting the drivers for my new Windows build. So when I went to the support page, something caught my eye. It said, detect PC, but this was a website. How could a website detect my PC? So the thing that struck me was that in my web browser, I had nothing installed yet. How could a website be able to identify my PC and find drivers for it? You know, it's one thing to detect that I'm running on Windows, but to find my model number, that seemed a little bit suspicious. So after clicking the button, I was led to this install page. Normally, it came pre-installed, but I upgraded it to an SSD and therefore had completely reinstalled Windows, uninstalling the bloatware. So after installing the program, I decided to snoop around and try to see how it was communicating with my PC. I found in Chrome's network debugging utility that it was connecting to localhost at port 8884. The parameters expired, and signature hinted at some sort of verification system for each request was in use. When reversing to JavaScript that was actually making these requests, I found out that it grabbed a list of signatures from a page that Dell exposed publicly. These signatures were the same across machines, so that anyone who made a request to the signature page could get a valid signature to make a request. So when I saw that it was making a request to port 8884, I checked that port out in Process Hacker, and I found out that the SupportAssist agent service was the one hosting this port. And what Dell was doing was exposing a sort of REST API. It would allow communication from the Dell website using a strict access control allow origin header of https://dell.com. And this was to prevent other websites from making requests to the client. So when I found an available update, a post request was made to the download service API. The request that was generated made me feel like the software might be insecure by design. There were several red flag parameters, such as location and path, which concerned me because it felt dangerous trusting this much user input. Some red flag parameters were location, path, run, restricted, and is secure. I'm not sure why Dell would trust user-supplied input for the download URL. For example, the Intel driver in SupportAssist takes a smart move of taking in an identifier for the update instead of just trusting a download URL provided by the user. So the server was programmed in C#, and it made it really easy to decompile and see what it did. Using a simple tool like dnspy allowed me to look at a lot of the source code for the application. So before the thread holding the web server even began, the agent itself found the physical session that you're logged in using the WTS get active console session ID Then it tried to grab the token of the session. So the user that was logged in at the time of the service start would have its token duplicated, and the web server would start using that token. It checked to see if the token was linked to an elevated token, and if there was an elevated token, it would duplicate that instead. Before the download request is processed and the agent begins downloading, there are some integrity checks that the request must pass first. The first check is make sure that the request was made from the local machine. They check this by seeing whether or not the request destination is a loopback address. Think localhost or 127.0.0.1. The second check, make sure that the refer header contains a whitelisted host. The third check they do is make sure that the signature and expires parameter provided in the URL are valid for that specific API method. So after passing the generic checks for the request, the next step is to call a method called callService method to dispatch your API call. When callService method receives the service and the API name of download and auto install, the method first grabs the raw post data from the request and sends it to the download service logic class. The download and auto install method will then call a separate method to handle the deserialization and verification of the provided JSON data. So next up are some more specific checks in the request. The agent makes sure that the provided download location does not start with http:// and that only specifically. If it does, it'll call the C# replace method on the string to replace all instances of http:// with https://. To make sure an attacker doesn't supply their own server, Dell has a hard set of whitelisted download servers, which it compares with the host of the download URL. If the request passes these final checks, the agent will download the file using a C# HTTP web request and actually execute it. So the final steps to execute your program. The agent does this by using a method called launch process and read standard output. This method will call onto a command prompt to start the downloaded program. So this meant that it would go from the Dell SupportAssist server, start a child command prompt process, which would start your download process after that. So looking at how we can exploit this, we have to first look what we covered. In order to make a valid download request, first we need to make the request from a local machine. I did some research to see if the request could be made from someone on the network, but it seemed like there were too many barriers to be able to make a remote request from the same network. We need a whitelisted refer header, meaning that our request needs to come from a Dell website. We need a valid signature and expires parameter. We can't have our download URL start with http:// because if we do, it'll get stripped out. Finally, we need to provide a download URL that has a whitelisted host. So fortunately, all of these checks can be circumvented. The first check, making sure whether or not the request is from the local machine, can be bypassed by making the request from a website, because it'll appear as though the browser is doing the request. The second refer check can be circumvented by making the request from a Dell website that we connect to using HTTP, allowing for DNS spoofing. Cross-site scripting would also work for this, but the issue with that is that further on, it won't work out. The third check can be bypassed by grabbing signatures from the page Dell exposes to everyone. The fourth check about our download URL not starting with http:// can be bypassed by not having our URL start with http://, rather space http://, http://, or just all caps http://. There's so many variations for this. It was a really rudimentary check. It was case sensitive, and it just seemed easy to bypass. So all we need to do is ARP and DNS spoof the victim, and we can successfully bypass all checks leading to remote code execution. So here's a video. Okay, so it might be a little bit hard to see here. This is Kali Linux, obviously. So the first thing the attacker has to do is actually start the proof of concept. So we can see here the first thing it does is starts a fake web server, starts ARP spoofing, and then it'll send the ARP packets to the victim. and then it'll actually start DNS spoofing. Then what the victim has to do is visit the website. Now you might say, Bill, you're going to need to have the victim on your same network and they have to visit a website. How are you going to do that? It seems pretty complicated. One easy way to do that would be through an evil AP attack, where maybe you have a fake router that someone connects to and you have a captive portal that will automatically launch when Windows detects that there is a captive portal. And at this captive portal, you can have the exploit. So when the victim visits a malicious website, we'll actually see in the proof of concept that the attacker receives confirmation about the exploit being delivered. You'll see a bunch of requests saying that the DNS request was received for the Dell RCE attack. And then we'll actually also see that the exploit binary was requested. That's key. That's what the service was requesting. And then finally, the malicious program is launched. And as you can see here, our malicious program is the calculator. Okay, that's the first bug. So going to the next bug, can you find out what's wrong with these three pictures? So on the left, we have a process called SupportAssist AppWire.exe, an unelevated process. In the middle, we have the same SupportAssist agent process, except we see that it has a full control thread handle to a process called SupportAssist agent.exe. Finally, on the right, we have that SupportAssist agent.exe process running as NT-authority system. So an unelevated process has a full control thread handle to a system process. That's definitely not good. Let's see why this happens and how we can exploit it. So starting 14 days after Dell SupportAssist is actually installed, the agent will start showing you these helpful messages, letting you know that you should run their software to quote-unquote optimize your PC. This notification ends up being created by the unelevated process we saw on the last slide, SupportAssist AppWire.exe, which gets launched by a method called launchUWP_app. So launchUWP_app takes in an application name and arguments to launch the application within its parameters. Next up, it'll iterate all Explorer.exe processes and grab its token. Finally, it will start the application using createProcessAsUser, passing the token of the Explorer process. Can you find a vulnerability in this picture? I'll give you a few seconds for those interested. So the issue with this code here is that inherent handles is set to true. So what this means is that all of the inheritable handles in the system process will be inherited by the child process, which runs using the Explorer token. Now Explorer runs as unelevated. So what this is doing is creating a child process using an unelevated token and actually giving it inheritable handles. In our case, that was the thread handle which was set to be an inheritable, meaning that the unprivileged child process ended up getting a thread handle to the system process. So let's start exploring how we can exploit the leaked thread handle. One of the easiest ways to execute code with just a handle to a thread is to use something called QUserAPC to call load library. So there are some requirements to call this. First up, we need to be able to predict the location of a buffer that contains a path to a file I can access. So this means I need to have a memory address where it'll have a DLL name that I can pass to load library. So what this means is that since load library takes in a DLL path, we're going to need to somehow map our DLL name into the memory of the system process. So it turned out while investigating that load library API call doesn't care about the extension of the file you're trying to load. It can be any extension, it will still load it. So the path we need to find just needs to be something we can access. And the file path doesn't need to be .dll or .exe. It can be really anything. Once we pass that to load library and write our DLL to this path, it'll load our module into the system process. So what I did first was I used Process Hacker's string search functionality to find strings. I filtered for the string C:\\. And the address of the first string really confused me. It says it's 0x180.163.f88, but the thing that caught my eye was the 0x180. I quickly checked the modules list for the process, and I found out that SQLite3.dll was actually loaded with a base address of 0x180000000. So, was ASLR disabled? Looking at the SQLite binary, I found out that indeed it was. The module itself doesn't have the ASLR characteristic, which means that unless it's forced, it will always be loaded at the base address 0x1800000. This meant that anything inside this module was completely predictable. It would be at the same address every time, even after restart. In this case, it was the string cdev SQLite core SQLite3.pdb, which is a path we can write to. And since we further knew beforehand that load library doesn't care about the extension of the file, it meant that this path would be suitable for an exploit. So the next issue I found when trying to make an exploit for this is that the thread wasn't actually responding to my queueUser APC call. And this was because it was in a non-alertable state because it was waiting for a service control handler message. And so I looked at the service in Process Hacker, and I found out that all interactive users had the permission to actually interrogate the service and actually send a service control code to the service control handler. So this meant that we could get it out of the non-alertable state, and then to make sure that the queued APCs were executed, we can set the RIP register of the thread to NT-test alert, which will empty out all queued APCs. So here's the video for that. So first, we need to wait for the notification. And we can see at the bottom right, it says optimize your PC, run SupportAssist, now to ensure that your PC is up to date and running at its best. So then the exploit goes quite fast, but we'll quickly see here that I am NT-authority system. So looking at these three command prompt windows, we can see that the first process on the top left will actually search for the SupportAssist AppWire binary. This is the unelevated child process that was created and has the leaked thread handle. What we'll do from there is actually get into that process's context and try to find the thread handle. That's the second command prompt window, by the way, the child process. It will actually try to find the thread handle that was leaked. And then all it does is it'll queue user APC on top of this process, on the top of this leaked thread handle, which will call load library using that predictable PDB path that I mentioned earlier. So this causes load library to load our module because we stored it at that SQLite path. And then our module will start a child command prompt process. And since it's from a system service, it'll inherit the token of the service as well, which is running as NT-authority system. So when reverse engineering the Dell SupportAssist agent, I had some privacy concerns. So on most exceptions, this agent itself will tell Dell servers exception details along with your service tag. When a file is executed for the download and auto install API, Dell will send the file name, the service tag, the status of the installer, and the logs for the execution of that installation to their servers. When you scan for any driver updates, any updates found will be sent to Dell servers alongside your service tag. Whenever Dell retrieves scan results about your BIOS, PNP drivers, installed programs, all of it gets uploaded to Dell servers. Every week, your entire log directory is uploaded to Dell servers. Every 2 weeks, Dell uploads a so-called heartbeat, including your device details, alerts, software scans, basically pretty much everything about your system, and it'll of course include your service tag. So you're able to disable some of this tracking, but the thing that worries me is that this is enabled by default and is running silently on millions of endpoints. So Lenovo Service Bridge, the second vulnerability. Lenovo Service Bridge is designed to help with updating and troubles with your computer. It'll automatically detect your machine serial number and machine type. It'll download multiple files at once from the product download section. So unlike Dell SupportAssist, Lenovo Service Bridge is only installed when you go to update your system using their utility. But the thing is, if you install it once, it'll remain there permanently until it's uninstalled. So when I first opened this in DNSpy, I saw something kind of shocking. They were using a crude obfuscator for C# to attempt, I guess, security through obscurity. I wasn't quite sure because Lenovo is a pretty high company, and I didn't understand why they would steep to those kinds of levels and with the goal of security. And I was able to deobfuscate it pretty easily using public tools, but it was still interesting to see a corporation doing this. So when this application starts, similar to Dell SupportAssist, the Lenovo Service Bridge starts an HTTP listener, usually on port 5128. When the HTTP listener receives a request, the software begins by ensuring the refer header starts with a whitelisted host, and the request handler exposed several API methods. The one that caught my eye was OSDiag. So the whitelisted hosts include pcsupport.lenovo.com, datacentersupport.lenovo.com, and so the refer header has to start with one of these whitelisted URLs. So for the OSDiag API, the API starts off by checking whether or not this local app data Lenovo Service Bridge OSDiag temp file path exists. If it does, it'll go ahead and delete it. The API then instantiates a .NET web client and downloads the URL specified in the request post data as a diacab file. After the download has completed, it will actually start this diacab file and using the MSDT binary. So looking back at the checks we need to bypass, it's really not that much. So our refer header has to start with a whitelisted host. For example, the URL pcsupport.lenovo.com.builddemirkapi.me will pass because it starts with a whitelisted host. Lenovo did not implement a check on the URL passed in for OSDiag, meaning we can provide just a direct link to a cab file to download. Diacabs do need to be cryptographically signed, but they've been used maliciously a lot of times before. This is not the first time that diacabs have been used to deliver malware. So here's a video of that. So all a user has to do is go to a vulnerable, the payload website, the exploit website, and then, no, this is not up, by the way, for anyone curious. It'll automatically just instantly start a diacab. That's the diacab, ours is right there. And so obviously we can change the text, the logo there, we can change the icon, we can make it look really legit. So there is still user interaction required. The user interaction piece required to actually execute real code is them to press the next button. But once they press that next button and it starts doing the diagnostics, we have complete remote code execution. And so I just, my exploit was pretty simple. So you can do diagnostic utilities using PowerShell, and I just made it start command prompt as a proof of concept. And Lenovo Service Bridge does not run at privileged, so it doesn't really start an administrative shell, but it's still interesting to see. So if you go to my website and you have the service installed, all you have to do is press next, and then I have full compromise of your system. So it's pretty big. So Dell wasn't the only one with some privacy concerns. When a web server starts, Lenovo sends details about the port. On most exceptions, Lenovo will send details about the code that caused the exception. And in most API methods, Lenovo sends details about the request. So looking at the disclosure process for these two companies, Dell took over 6 months to address a remote code execution vulnerability. Yeah, this was my first time working with a big vendor, so I wasn't like 90 days until I disclosed or anything like that. But it was pretty big. And for their local privilege escalation vulnerability, they only took a month, and it was pretty simple. They just had to set inherit handle to false, so it wasn't a complicated patch. And Lenovo took less than 2 weeks to fix the remote code execution vulnerability. So some thanks go to Alex Ionescu, which is my mentor, and he also works at CrowdStrike, the company I interned for this past summer. And he helped me a lot with the Windows internals parts. And yeah, he literally rewrote Windows at some point, so he's pretty knowledgeable when it comes to that. And then Rick Martinez was someone at Dell I was in contact with, and helped smooth out any of the issues we had. And yeah, that's pretty much it. Here's some contact. Follow me on Twitter, check out my blog, and I hope you enjoyed the talk.